Hey, this is Soman from neosystems.com. Today we'll be seeing the CMOS stick diagram. We'll also consider the depletion MOSFET, its stick diagram, and an example question. CMOS follows a certain color codes while drawing the stick diagrams. These color codes are: metal follows a blue color code, polysilicon red color code, metal contact a black color code, p-type doping a yellow color code, while the n-type doping with a green color code. Steps to be followed during the stick diagram. There are basically three steps to be followed. First, draw the schematic diagram. Second, understand the nature of devices to be used, which mainly includes is it a PMOS or an NMOS, and final step is to find out the exact color code which is to be used while drawing the stick diagram. We now begin with the schematic diagram of the depletion MOSFET. The depletion MOSFET is shown in the figure. It contains a depletion region which allows the current to flow between the junctions without any gate biasing voltage. This is because of the channel which is present in the depletion MOSFET. Hence, it does not require a gate biasing voltage. We begin with drawing the VDD and ground connections for the depletion MOSFET. Since these are metal connections, we represent by blue lines. Next is the two NMOS. Since the NMOS have an N-type substrate, it is represented by a green color. The next we move on to the inputs. The depletion MOSFET has inputs which is directly shorted with the output and the other input as Vin. We proceed on to drawing the depletion region. Since the depletion region is the main part of the depletion MOSFET, it is drawn with a dotted rectangle, and since it is a P-type region, it is represented by a yellow color. We finally proceed on with drawing the Vout connections and placing the metal contacts wherever necessary. Since we have finished drawing the depletion MOSFET stick diagram, we now move ahead of solving an example. We shall draw a schematic diagram of a function f is equal to x the whole multiplied by y plus z plus x into w. In NMOS, the dot is treated as a series function whereas plus is treated as a parallel function. It is exactly vice versa to the PMOS. The symbolic representation of NMOS and PMOS are shown in the figure. You can see that both NMOS and PMOS are exactly likely except for the bubble which is at the gate. Now notice that the source and the drain of the NMOS are exactly opposite to that of the PMOS. Now what do we mean by a series and a parallel connection? P1 and P2 are facing each other whereas N1 and N2 are connected one after the another. Since P1 and P2 are facing each other, they are said to be connected in a parallel, and N1 and N2 are connected one after the another, which means they are connected in series. Well, what we have exactly drawn now is the NMOS NAND gate. Since CMOS deals with reducing the expression, we take an x common out from the expression. Hence, we can reduce the expression to x the whole multiplied by y plus z plus w. We now begin with drawing the schematic diagram for the given expression. As a rule of thumb, I always draw the NMOS section first, followed by the PMOS section in a bottom to top approach. As in the expression, y, z and w are implemented by a plus function, I connect them in parallel. However, x is implemented by a dot function, so I connect x in series with y, z and w. In PMOS section, actions are reversed. We see that y, z and w in the PMOS section are connected in series, whereas x is connected in parallel. Make sure that after drawing, you label the transistors, the VDD connection, the Vout and the ground. Also please notice that while implementing a plus in PMOS, it is series, and implementing plus in NMOS is a parallel. Implementing a dot in NMOS is series, whereas implementing a dot in PMOS is a parallel. Let us summarize the steps for the expression f is equal to x into y plus z plus w into x. First, we need to start with the NMOS section with the bottom to top approach. Then, draw the transistors as per the convention, which means dot in series and plus in parallel with the NMOS. Label each transistor with the variables mentioned in the function. Label the power supply, VDD and ground. For drawing the stick diagram, we follow a rule known as Euler's path. In Euler's path, we represent each NMOS transistor with a curvy line. Second, we represent each PMOS transistor in a curvy line. We select the path such that no line is traversed twice. For example, in this equation, we select the path x, y, z and w. As seen by the arrowheads, in the NMOS section, we move from x to y, then from y to z and z to w. Please see that no line is traversed twice. The arrowheads also remain same for the PMOS section, that is from x to y, y to z and z to w. Please label the drain and the source for the NMOS section and the PMOS section. Also notice that the drain and the source for the PMOS is exactly opposite to that of the NMOS. Please see the figure carefully for the labelings of the drain and the source for the NMOS and the PMOS. From the Euler's path, we begin drawing the stick diagram. First, draw the VDD and the ground connections. Following them will be the XYZ W polysilicon layers. Yellow color represents P substrate in the PMOS section and green color represents NMOS N substrate. We label the PMOS transistors from drain to source by exactly following the sequence from the Euler's path. Please notice the arrow in the PMOS section was moving from drain to source in the X transistor to source to drain in Y transistor to source to drain in the Z transistor and finally source to drain in the W transistor. Whereas in the NMOS section, the X transistor arrow was moving from drain to source in the NMOS to Y transistor drain to source to Z transistor source to drain and finally drain to source of the W transistor. We also connect the VDD and the ground lines. In the PMOS section, the X and Y transistor source are connected to VDD. In the NMOS section, Y and Z transistor source are connected to ground. Also, the W transistor source are connected to ground. We get all this information from the Euler's path. For the out, we connect drain of X transistor in the PMOS section and the drain of W transistor in the PMOS section. From the NMOS section, we connect the drain of the X transistor. This information can be found out from the Euler's path.